for H. All right, 1. Reason 1. Minus 1 over n log P of xn converges to H, the entropy. So the entropy gives you your exponent in how fast this behaves, and this is with probability 1. And in probability and in distribution and so on. So it's the answer. I'll put a dot over here, 2 to the minus nh. Dot over the equal means this is correct to first order in the exponent. First order nh, second order terms of order little o of n. All right, 2. nh plus epsilon bits suffice to describe this random sequence on the average, and with high probability exactly this. Look, I know that the novel War and Peace by Tolstoy does not consist of independent, identically distributed symbols. That would be a monkey at a typewriter. But there is a tremendous amount of dependence among them. That's an example of, well, stretching it a little because ergodic has a precise mathematical meaning, and War and Peace is whatever War and Peace is. But if War and Peace is an ergodic process, then it has an entropy rate. And when you find out what its entropy rate is, the innovation in entropy per unit time, you find out it's about 1/4. This is typical of all the languages. A novel in German, a novel in English, a novel in Russian, tends to be compressible to 1/4 of the number of symbols. So, I'll give you an example. Let's flip a coin that has probability of heads 0.11, 11%. The entropy of those IID coin flips is 1/2 a bit per flip. So if I want to describe this 1,000 coin flips exactly, 500 bits should suffice. There are only 2 to the 500 typical sequences, not 2 to the 1,000. So now we have H gives me the probability of a sequence. It gives me the number of bits needed to describe it. Those are pretty good reasons for H. 3, 2 to the H is the effective alphabet size English has 27 characters, let's say A through Z plus space. Let's forget punctuation and capitalization. So the alphabet size is 27. But The effective alphabet size is since it's compressible by a factor of 4, the effective alphabet size is about 3. It's sort of between 3 and 4. If I had an alphabet with just 4 symbols in it, then I could express anything that I'm likely to encounter in English literature. Huh? So that's what I mean by effective alphabet size. Now, 4, here's another good reason for H, and this is where it first came up in Boltzmann's considerations. N choose K. So I have N objects, and I want to choose K of them. Or if I wish to put it another way, I have N sequences of 1s and 0s, and there are K 1s in the sequence. How many such sequences are there? Well, I choose them this way. This is N factorial over K factorial times M minus K factorial. Now, let's use the fact that N factorial is equal to N over E to the N. That's not quite true. This is due to Stirling's formula, and you can get tight upper and lower bounds, and this is true to first order in the exponent. When I plug that in, I get N over E to the N, N1 over E to the N1, N2 over E to the N2, or N1 plus N2. I guess I mean K, don't I? Sorry. K, 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 K. K here, N minus K. K power, M minus K. Another thing you can't read. Well, the E to the N and the E to the K, or the E to the M minus K, they cancel out. And we're left with N to the N over K to the K, M minus K to the N minus K, which is precisely equal to 2 to the N times H of K over N, N minus K over N. Not approximately, precisely. This is approximate. This is precise, and that's precise. So just check it out. So in short, the number of ways to throw K1s down in N places is 2 to the N times the entropy of K over N. So entropy comes up naturally as the expression for what a combinatorial coefficient is. In fact, if I had N choose N1 through N sub M, N factorial over the product of the N sub I factorials, then I get 2 to the N H of N1 over N through N sub M over N. So that would cause H to arise naturally. And then 5, typical set has 2 to the n h elements. Again, referring to xi as being independent, identically distributed. In other words, what we've done is we've taken this whole set and we've found essentially the set, the smallest set that has probability nearly 1. We've squeezed all the randomness down to a uniform distribution over this. So you can see how it's going to make a lot of analysis of questions, data compression with an allowed distortion, communication, etc. It's going to make a lot of questions easier because of it. Now, let us do finally this. What about dependent processes? So we have xi. And we might have a Markov chain. x1 goes to x2, goes to x3, etc. And these all according to p of x2 given x1. Similarly here and here and here. So a typical Markov chain might be you're in state 1, or in state 2, and you go here with probability alpha, stay here with probability 1 minus alpha, and if you're in state 2, you come back with probability beta, and stay here with probability 1 minus beta. How random is such a process? Well, there are two notions of randomness for this having to do with entropy. One is, let's calculate the entropy of n of them. How fast does that grow? Well, if it grows linearly, then this should go to what you might call some limit alpha. So that's idea 1. Idea 2 is, let's look at the entropy of xn given x1 through xn minus 1. We don't need to divide that by n. It's the amount by which your entropy increases. Oh, excuse me. It's the residual randomness in the next term given the n minus 1 past. I don't know whether this converges. But I would hope they both converge. And what we'll show next time, and then we'll do a number of other things, is we will show that both of these converge for a stationary process, not just Markov. For any stationary process, both these, the entropy grows linearly, or the residual entropy goes to a limit. And furthermore, these limits are the same, and we'll call them the entropy rate for the process.